So my name is Avner Vengosh. I'm a geochemist. I worked on water. I study water chemistry from different parts of the world. Currently, my group is working in Vietnam, Morocco, and Ethiopia on water quality issues. And we are trying to understand the source of contamination of water by characterization of the water chemistry and isotopic fingerprinting. And I'm going to talk today about the energy-water nexus and going to focus on the two major issues related to coal and natural gas, which are the major component of the energy production in the US, as you all aware. And in fact, we are now in a very critical time in which the energy kind of trend production in the US, if you're looking in perspective, and we see now that natural gas exceed coal production, and it's kind of dramatic time after several decades of predominance of coal. And what I, in my talk, and try to engage you today is talking about the different procedure for coal mining, like mountaintop mining, which causing contamination of streams in West Virginia, for example, by selenium. I will talk also about coal ash. We usually think about coal, about CO2 emission, but there is a hidden, very important aspect of effect on the water, energy-water nexus, is the coal ash, and specifically if we try to install scrubber to protect the atmosphere from pollution of coal combustion, and it actually accumulates in the coal ash, coal production, coal combustion product, and eventually contaminate waterways. And I show you an example from North Carolina. And finally, I will talk about extensively about shale gas and some results that very extensive research we've been conducting here at Duke. So I'm trying to cover all. The first two will be very short, and I'll try to engage into the energy-water quality nexus. Now, there is a huge literature about the energy-water nexus in terms of water quantity. In our research at Duke, we have been focusing on the water quality nexus that has been somehow neglected, and we're going to show it. We are showing the different effect of those major energy production in the US. So mountaintop mining in West Virginia, for example, there are several labs at Duke that are working on it. So introduce the Julio lab, my group, and Emily Bernhard lab, each tackling different aspects of the research. We've published a paper in PNAS 2011. There is a paper now in review. And here we are trying to understand what are the impacts of mountaintop mining on water quality in West Virginia. And this is an example of the research. There is area of that already reclaimed coal mining, active coal mining, and we monitored the water quality that's coming from streams into a major watershed from reclaimed and active areas. And we showed that the level of salinity of the stream increases with flow, and also the level of selenium is far exceeding any ecological threshold for the ecological integrity of the areas. And we actually see effects on fish tissues, selenium bioaccumulation, and actually morphological tissues in the fish. The next stage of research will move into actually studying the fish. And we are now beginning to measure a fish otolith, the fish ear, with the isotopic fingerprinting, trying to link what's being accumulated in the fish to the actual source of contamination. The next is coal and coal ash. Now, as geologists, there is a link between an ancient swamp, which was about 400 million years ago, which is under reducing condition, to the modern waterways of North Carolina. So what we, just to give you the concept, so during formation of coal in the old swamp, we have accumulation of different trace elements like arsenic, selenium, boron, and others. And once we combust the coal, those elements would be volatilized, but then captured through the fly ash. Now, if we have a scrubber, the affinity or the ability of this capturing is much more efficient, and we're actually moving all those contaminants, preventing air pollution into the coal ash. That sounds good. However, the coal ash is being stored in ponds, and upon interaction with water, it will generate effluent enriched in those elements, and they will leach into the water resources of modern water today. So this kind of a cycle is affecting the water quality. And this study has been conducted a few years by in my lab and Hasu Kim lab from engineering. So we collaborate on studying the TVA coal ash spill in Tennessee. We published several papers on that. And recently we published a paper, what's happened in North Carolina and the effect on water quality in areas. This is the study. We study any rivers and lake in North Carolina that is associated with coal ash ponds and evaluate the water quality, the effluent, the outfalls that are coming, but also downstream water in those sites. And we found that the effluent in the outfall are enriched in several contaminants, for example, very high level of arsenic, exceeding the drinking water level. But also we found, even more important, that elements like arsenic, they are not being part of the water system, meaning the dilution is not really an effective way to remediate the problem, because arsenic is being retained into the sediments in the river and the lake sediments, deposit in the bottom, and then under reduced condition is being released to the pore water about 10 centimeters depth at the bottom of the lake. And this is the place when the ecological change taking place and bioaccumulation of arsenic into the ecological system. And we found extremely high level of arsenic, for example, in those lakes, just in the middle of lakes that are being fed by effluent. The problem that we found in North Carolina, it's not only unique for North Carolina. There are about thousands of similar coal ash ponds through the country. And this is a problem that hasn't been resolved because coal ash is not being regulated in the United States. And only recently, we hope, following our study, we like to think that the EPA were just initiating a new proposal for effluent limitation guidelines. This just came out 2 weeks ago, and actually set a standard and a rule for a zero discharge rule that will stop contamination of waterways in the United States. And this is now under probably going to be a public response and debate onto that. The next is talking about shale gas drilling and hydrological fracking. This is a picture of a rag in northeastern part of Pennsylvania. This kind of a rag is very typical, common for shale gas. And here is a fence of a house that's living here. So basically, this kind of a landscape is taking place areas of shale gas development. Probably I don't need to talk here in this audience about what is shale gas and hydrological fracking, but in a sentence, this is a technology that has been known for many years, but the combination of vertical moving into horizontal drilling and hydrological fracturing, and able to release methane in very low permeability shale and release it into the well. The combination of this technology started about 2005, 2006, and kind of accelerated with massive production of shale gas. It's from basin in the United States, and the famous is the Marcellus Shale that we've been working extensively, but there's also other basins throughout the country. Shale gas is going to be part of the energy production in the US. Right now it's about 20% of the gas production, and expected to move up to almost 50% of the gas production in the United States into the next decade. So this is a very important resource. It's going also, I'm not going to talk about it now, but there is also the global aspect that shale gas is going to become a global commodity, and especially how you start to mobilize shale gas, it's another issue. And following this very rapid expansion of shale gas, there's been several issues about the environment. I'm not going to cover all of them, but just important to mention that the water utilization is a factor. The fugitive emission of methane to the atmosphere is really part of a serious debate, whether switching from coal into shale gas actually saving the atmosphere from fugitive emission. There is a debate about that. There's a strong group in Cornell that argues that it doesn't. There is issues of contamination of wells that I'm going to talk about, the fracking fluid, the different chemicals in the fracking fluid, air pollution associated, and health implication, quality of life, infrastructure, traffic, all those issues are very important, and of course the disposal of the wastewater that are generated during the fracking. All this kind of a very important issues, and as a result, we are witness today to one of the most kind of strong, probably everyone in this room have a very strong opinion about shale gas, and we see it as one of the most kind of strong debate about environmental issues. And very interesting, there's a huge information in the website. There's only maybe 10 peer-reviewed published publication of that. So there's a huge gap between what we think about it and what we know about it. So in Duke, our group in Duke tried to accommodate and to address some of the issues, and focusing on water that I'm going to talk here. And the kind of a two question we tried to address: does shale gas drilling and hydrofracking cause contamination of drinking water wells? And also, does disposal of unregulated, which is disposal of wastewater from shale gas, is not regulated. It's exempt for any regulation in the United States right now. What does it mean for the ecological system? And there's only health risk associated with that. So our group composed of people. I want to introduce the important people. Is the PhD student Nat Warner, Rob Jackson, Tom Dara, and Adrian Down, which is here. These are, Stephen Osborne was a postdoc previously in our group. And basically, our group has published several papers, mostly in PNAS. There's a new paper coming now next week in applied geochemistry. And I'm going to show you some of the highlight and the result of that. Again, we're only in the middle. It's not the idea to sum up all the research and what we know about shale gas. We not only attempt to say whether it's good or bad shale gas, but only to give you sharing some of the data that or the information that we have collected so far. So what we've done, we collected hundreds of water wells in Pennsylvania, West Virginia, Texas, Arkansas, and North Carolina. And we tried to build up a large pictures of understanding what does it mean to shale gas to the environment with respect to water. We collected hundreds of wells. The last counting was over 600 shallow drinking water wells from different parts of the country. We collected hundreds of surface water and also hundreds of flowback water and produced water, the wastewater that being generated during the industry operation. And basically, we measure a large spectrum of inorganic constituents, isotopes. We're using those isotopes as fingerprinting for tracing the sources. We measure radioactivity in the water, which is very important. And we also begin to also measuring noble gas, which is a new technology that kind of going to show the smoking gun for evidence for contamination. There's another group by Desiree Plata from engineering who is start to work also, and they are working on the organic constituents associated with produced water and the chemistry of that. So in a nutshell, result, we showing, and we think we provide evidence, that stray gas contamination is real, meaning that there is effect of contamination of well by methane, and you can lit the water on fire, as shown in Gasland and some other cases. But it's not always. So the new paper that is coming next week showing that in Arkansas, we don't see any evidence, any effect of shale gas contamination. So it depends on the geology, depends on the infrastructure. So there's no final kind of a rule for contamination based on our data. Here is an example of how we do that. We look at the well methane level and with respect to the distance to the nearest gas well, and we see that those wells located less than 1 kilometer are characterized by elevated methane level exceeding the equilibrium, which becoming the action level of hazard mitigation, meaning that you're not allowed to use this well. So if you are homeowners, having this level of methane is you cannot use this water, and there's a huge house economic impact for house de-evaluation as a result. We also show that those wells have different isotopic fingerprint, showing that there are different sources of methane arriving from well located next to shale gas well versus away from shale gas well. This is a much more elevated data, much more that we have generated since the publication of the first paper in 2011, and it's all repeating itself. We have now new evidence that will be part of the Nobel gas paper that we think that the leakage, that this contamination of methane is because of the infrastructure, because of leakage of methane from incomplete or of sealing, of the cement sealing on the shale gas, and the methane is escaping into the shallow aquifer, rather than actually inherent problem of escape of methane through the geological system at the formation, the shale formation to the shallow aquifers. So we have quite strong evidence that we are talking about problem in the infrastructure, in the integrity of the shale gas well, rather than a problem, which is a good news for the industry because it can be fixed. The second point of result, we haven't found in the hundreds of wells we examined, no evidence of contamination of fracking fluid of produced water. And this is very important. This is very in against many of people that think the water being contaminated. Using our very large spectrum of isotopic and geochemical fingerprint, we rule out any contamination at that far. Of course, that can be changed because the next type of evidence we found that there is hydraulic connectivity between the deep formation at a depth of 1 to 3 kilometers at depth to the shallow aquifer, at least in the area that we investigated in northeast Pennsylvania. So we have evidence that natural flow of saline water from depth can flow naturally to the system, and that's very important because it meaning there is potential for contamination and and that could actually lead for future contamination. We based this very strong assessment based on actual occurrence of saline water in the surface, which has the isotopic and geochemical fingerprint of the Marcellus brine at depth. And finally, we found that unregulated disposal of wastewater actually causing long-term ecological effect on health risk. Not only we found that there is a huge level of salinity. For example, the salinity that's being discharged from a treatment plant in a study that we are investigating in detail would have a 200,000 milligram per liter is very different from the upstream, which is less than 100 milligram per liter. We see several orders of magnitude enrichment of salinity. And not only the salinity, we found that the sediments at the rivers are enriched in a high level of radioactivity, orders of magnitude higher than the upstream and the background sediment. So we are finding that not only the water being contaminated, but also the sediments of the river with a very highly radioactive element which is going to have a half-life of 1,600 years. We are actually saying we're building the legacy of contamination that's going to stay there for the next thousands, about 7,000 years to be exact, in between it goes down. So this is a long-term legacy of environmental effect. What we did in our study, and this is the part of the PhD student of Nat Warner, is to build the tracer, the natural occurring tracer, to be able to delineate the source of contaminants. And we are now able, for example, to discriminate between the effect of wastewater coming from unconventional wastewater from the Marcellus versus other source of wastewater like a conventional oil and gas wastewater, and they have a very distinctive isotopic using boron and strontium isotopes. All this combination enable us to delineate the source of contamination pretty well. Finally, kind of the conclusion to take home message. Based on our study, it's obvious that coal is still going to stay with us in the next generation, although it's going to change, going to be reduced, and we are now seeing how shale gas is taking its place, but it's still there. We have very strong scientific evidence that coal mining, coal combustion, and shale gas exploration have significant impact on water resources. This kind of effect should be addressed, and kind of a challenge to for the economists in this room, how you quantify the effect of contamination in terms of the economical costs and how it's balanced through the advantage of having those cheap coal. It's not cheap because we have a huge environmental impact, but it's important when we're talking about the US energy security, there are direct and indirect effect on the environment and kind of a long-term implication of the ecological system and human health that should need to be addressed. So we are only in the middle of our research, and thank you for your attention.